me take my hand, push my knees, shall we dance up here? You know I love you, just like I'm having. You make it better like that. Don't think I always feel like I'm from body. Who wants to get it? I don't care what I'm with my baby. All that is you make me feel maybe I am somebody. I think the better time when I'm with my baby. I don't care as long as you're holding. You can see me anywhere. You make me feel love by somebody. I feel the better time when I'm with my baby. You gotta probably we don't wanna be on. That's all over there. I said, I got some jeans or get some bad guy. Most people are around. We have no big time. You got souls, man, souls. You know what? It's crazy. You don't really know mine. You keep that like that. Yeah. Yeah, it's my question. Hey, oh yeah, yeah. When we were in the started, but now we think that we should stay. Cause I don't care what I'm with my baby. All the bad things to me. Making me feel like maybe I am somebody. I feel the bad things when I'm with my baby. Oh, yeah, so I don't care. As long as you just hold me, you can take me in my head. Making me feel like I'm lost by somebody. I can't help the bad times when I'm with my baby. I don't like nobody but you. You're the only one. I don't like nobody but you. I don't like nobody but you. I hate everyone. I don't like nobody but you, baby. Yeah, 'cause I don't care what you're doing, my baby. Yeah, I don't care about that. I'm just you make me feel like maybe I am somebody.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 50,000 components on a chip.
Yeah. Guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over. The future is peril. Single cores are not getting.
Must be recorded or not. It will be, yes. I have a different class after. Thank you. All right. Welcome to CSE 142. You're here for CSE 142, right? Yes. Okay. Yeah, I can't believe there is a class in person, right? It's hard to believe nowadays that people want to in-person class, but I prefer in class a little bit more because I think there will be more interaction. And I'm glad that you guys are all here today. But before we start, I know people are coming in and out. So why don't we start with this 3 questions, and a lot of you also have answered the same question while you have this. So first of all, the first thing that I want to know about you is, what's your name? Like, what's your name? So, let me start from Ivan, right? I just know you. So, okay, so now let's have a like probably 10 to 20 seconds, quick introduction about yourself, your name, right? What's your favorite topic in computer science and one fun fact about you?
My name is Ivan. I'm going to history learning and AI topic in computer science. And fun fact is I actually know PVC myself.
Oh, really? So you are taking a conversation class at UC San Diego, but you are actually at UC Riverside. Really? Okay, so we actually have the St. Holmes campus.
Merced.
Is this one your hometown, like San Diego, your hometown? Okay, I was here in Riverside
Merced.
in fall, right?
No, Merced.
What?
Merced.
Merced. Okay, Merced, okay. Sorry, I heard.
Yeah.
Yeah, that's far away. Okay, nice meeting you. All right, what's your name?
Hi, hi everybody, my name is Brendan Devlin. Interest of mine, I really like Excel spreadsheets and that kind of stuff. Guess kind of can get me related to programming. What was the third question?
Fun fact about you.
I'm interested in spreadsheets.
Okay. All right.
Hi, my name is Yao, and I'm a senior student. Content and birthday is November 11 at 11 p.m.
Really? Okay. It's a pretty, it's right now a day for shopping, right?
Oh yeah, hello everyone, my name is Dr. Tao, and I don't think I guess I'm one favorite topic in computer science, but right now, like most in full stack development, I'm learning more about that. And to kind of like just give you a back about like birthday. My birthday's on February 28th, 2002, so it's going to go.
Oh, wow, everyone has an interesting birthday. What's your birthday? Oh, the day after, well, that's also a special day, right? Okay, what's your name? Fun fact about you. Okay.
Hi everyone, my name is Dylan and I'm going to be a leader today. A topic I'm interested is maybe automated system.
Uh-huh.
And a fun fact about me is I'm that.
Okay. I'm left-handed too.
It's Jack, I'm a fourth year, and the topic I like to make is learning development. Fun fact is I don't like fruits.
You don't like fruits? Oh, really? Any kind of fruits? Okay, that's fine, because sometimes people tell me about why people eating fruits, it's just a lot of sugar and water.
Like my favorite.
What's your favorite topic in computer science?
CUDA parallel program.
Okay,
And why I took 1.2.
oh, actually, fun fact.
Yeah,
I know why you take 142.
Fun fact is I like to play games.
Okay.
Hi, I'm Thomas. I guess my favorite topic in computer science is, I guess, that of distributed systems.
Mhm.
And a fun fact about me is that I'm actually a chemistry major.
Oh, wow, okay.
Yeah, hi, I'm Hamid. My favorite topic is like HTML and fun fact is like I'm speaking coffee. I like spending a lot of time making coffee every day.
What's your favorite coffee shop on campus, or just don't go to any?
On campus, like there's only one good enough. Like
For a lot?
yeah, it's like the only one good.
Okay.
The rest are bad. So,
Okay.
Hi, my name is Aishi, and I'm a fourth year university student. And my favorite topic in computer science probably counter. So I'm very certain that after this discuss, it will be my favorite topic.
Okay, I'm flattered, I'm flattered.
And
Thanks.
fun fact is I thought finance is my next computer science.
Okay. Okay, what's your name?
My name is Jack.
Okay. What's your favorite topic in computer science?
My favorite topic should be web
For the same.
Okay, fun fact about you.
I'm fine. I play golf.
Oh, wow.
My name is.
Favorite topic in computer science? Nothing? Nothing? Then why are you majoring in computer science?
Cause I like it.
You like it, okay, overall, right, no spatial, nothing spatially separate, but everything, okay, fun fact.
Kind of, especially on the bottom part of the bidding system.
Okay. Yeah, yeah, fun fact. About you. Fun fact. Okay, you're not fun at all, okay, come up with one,
Yeah, sometimes I'm thinking.
okay?
Yeah.
All right. How about you?
My name's Fernando Teo. My favorite topic would be circuits or low level design.
Oh, wow,
But it's just some stuff.
are you an EC major?
Yeah, no, not EC, I'm a CSE, but it's computer engineering. So
I see, I
emphasize. And fun fact mine is that I have a hairless dog.
Oh, really?
Yeah. So you know the Mexican hairless dog?
Really? But how did it survive during the winter?
Just keep it inside, I guess.
Okay. All right. How about you?
And my favorite topic would be, machine learning and, networking.
Uh-huh.
The top that is, I'm not very interested in.
That's fine. All right, how about you? What's your favorite topic?
Oh, I think it's AI, and a fun fact is I'm the agent now.
Okay.
My name is Henry. My favorite topic is data analysis.
Okay.
Something about me. Math major.
That's better. Okay.
My name is Michael, very popular. Sales number,
What's your theory? Remind me about that.
so program language for the,
Wow. I remember that.
yeah, fun fact is, I'm a physicist.
Oh, wow. One major. Okay, good. Not physics, not chemistry, not math.
My name is Catherine, and I'm joining the show. And we're going.
Okay, that's really great. What did you do during the gap year? Is that okay to share? I see. Okay, how about you?
My name is Yaren. I like cloud architecture. And sometimes that I've lived in the forest.
Oh, what are the four states?
Here, Washington State, New Jersey, and Virginia.
Which one do you enjoy? Wow, actually, that's four different regions, right? New Jersey is like, the big New York area, and Virginia, kind of south, but also not south, right? And Pacific Northwest, and now the West Coast. Where do you enjoy the most? Really? How come?
So I live right next to DC, so I'm not actually working south, but I think it's nicer and lighter and.
I see, because I lived in North Carolina before, and I'm here, so there's a reason for that. Do you think I'm going to forget you?
Hi, my name is Lee. I'm interested in software stuff in general. And fun fact about me is I took your class before when you were in UC Riverside. CSE142.
Really? Oh, really? Okay. All right, so, okay, so people online, any of you would like to share? Oh, I saw some. It's hard to hear. Well, so anyone online would like to share? Anyone would like to share? Would like to share? Okay, some chat. Are we listening to in-person class right now? That is true. And well, can someone online unmute and let us know? Well, can people online unmute themselves?
Hi, I can hear.
All right, you can hear me. Okay.
Yes, I'm Roman. I'm a senior student at UCSD. My major is computer science, and I'm taking this class to fulfill my core.
Okay.
Yeah.
Yeah, I know this. Right. What
Yeah.
fun fact about you?
Fun fact about me: I'm new to San Diego,
New
and
to San Diego. So you are actually in town.
what?
So you are actually in town now.
Yeah.
Okay.
So I'm exploring. Yeah.
Okay. All right. Okay, so if anyone else online would like to share anything about you?
Hi, my name is Hong Yuan, and I'm an international student, junior year, computer science major in UCSD, and my interest is natural language processing, and I take this class because I want to fulfill the requirement for my major.
One fun fact about you.
Fun fact,
Yeah.
I can't come up with one now.
Okay, well.
That's most fun fact.
Okay, that sounds
yeah.
fun. All right, anyone else online? Okay, at least for people online, well, so just want to let people online know this is a synchronous session with the in-person in-classroom class. So if you have any questions for people online, feel free to unmute yourself and ask, because if you're in the classroom, you will see that most of the time I'm not in front of my computer. So if just raise your hand, just type in the chat, I won't be able to see that. So just unmute yourself. But before you unmute yourself, make sure that your background doesn't have any awkward stuff. All right, so okay, so all of you, or most of you already filled a survey before we start the class, and a lot of you share your name so that I know, well, we have a very diverse group of students here, and sometimes why? Which one? All right. So, well, a lot of you might think, well, I talk a lot about yourself, right? But how about myself? So my name is Hong Wei. I'm currently an associate professor at UC Riverside. That's my job during the fall, spring, and winter quarter. But summer session, I typically spend my time in UC San Diego just because I love San Diego. And I spend sufficient amount of time at UC San Diego. I got my PhD here. And I live in here, so I know how you guys feel being a student here, because I were a student here, and I also spent a lot of time in the dungeon. So I know your feeling. I got your feeling. So if you have any questions, even outside of the class, feel free to reach out to me. I will try my best to help you. And so this is my website, and I have if you want to reach out to my email address, it's either like htseng@ucsandiego.edu or ucriverside.edu, both will work out. And this year I did something special in my first 3 months, because I just got tenure, which means that I'm unfireable in a tenure system. So the very first thing I did. So, I didn't even talk to anyone in my department before I got tenure, but, the very first thing that I did after I got tenure is that I asked my department chair, hey, can I take a leave to work at Google, because that's something I do like. So I spent 3 months at Google, and I worked for TensorFlow Lite. So some of you might think, wait, you're a computer science, you're a computer architect. How come you are working for TensorFlow, right? So you will figure that out later. So, and my research interest is actually general purpose computing using AI ML accelerators. And I also build intelligent storage devices and have done quite a lot of research on near data processing. And I'm also interested about VR stuff, because I used to play a lot of games before I became a professor. So if you want to be a gamer, don't be a professor. And so I have a project called OpenUVR. If you're interested, you can Google that and with my name. And fun fact about me, I was once considering a career path as a singer, but I'm here, right? So the trial is not successful, and don't Google my name on YouTube. It's awkward. All right. Yeah, but that are some good memory, and I'm also a big anime fan, right? So sometimes if you are in some anime related event like Anime Expo, that's what I look like. And okay, so your favorite topic in computer science, a lot of you point this out, right? So this is also the word cloud that I generated from the survey. And well, algorithm is a big one, security is a big one, machine, but I say machine here is definitely not machine assembly or machine organization. It should be machine learning somewhere there. Learning here. Oh, top left. Oh yeah, machine learning, right? So these two are together, right? Artificial intelligence, right? So I know this is what you guys learn, and you guys are really honest. I really appreciate that. And in fact, your preference is aligned with the general trend in computer science. So the 5 top trend in computer science research are indeed AI and robotics, data analytics, computer assisted education, bioinformatics, and cybersecurity. So there's nothing wrong to say, well, my favorite topics are this, because they are indeed the most trending ones. And being someone at Google for the first 3 months is actually pretty interesting, because that was the first time that Google interfaced the challenging of the change of user-computer interaction. So there is something called ChatGPT. And the right-hand side is Google's version of ChatGPT called Bard, right? So, and Bard, I believe, is launched in February, and that was the time that I feel like sometimes lucky that being at Google at that time, because you see the whole company is changing itself from a search company become a completely AI company, and everyone is thinking about how to do like large language models, and every project has to be related to that. And unfortunately, the reason why I'm here is because I cannot relate my TensorFlow project with that. So that's why I'm here. Otherwise, I would probably get more money from Google to pay for my mortgage. But first of all, right? So if you ask Bard about what's the most popular topic in computer science, Bard would definitely tell you. Or you ask ChatGPT, right? You can see that AI ML or data science cloud computing, right? For ChatGPT, they will also give you the same answer, right? So they have the answer pretty aligned with you guys, right? And the last question is that okay, everybody is interested about other topics, and why are you taking about CSE142, right? And this is the word cloud I generated from your response, right? As you can see, right? First keyword requirement, the second keyword require different sense of compare against require, right? Requirements, okay, rule of requirement, right? So requirement is probably the main reason why you're taking this class. And today, as the first lecture of CSE 142, we definitely want to turn your mind around why you should take computer architecture. So as a computer scientist, right, I know these are a lot of things you care according to your Google Forms, right? You care about algorithm, you care about the best data structure to use in your program. You care about if I want to have a teamwork, how to make a good collaboration using those software engineering tools. And you care about what programming language would easily help me to achieve the goal that I want to achieve. And you probably also care about user interface, right? And if I ask you about computer architecture, this is really right? You don't care, and most of people don't care about computer architecture. So, and what really computer architecture is, right? So, if you try to Google it on, or if you try to look up from a dictionary, this is the this is the definition of architecture. And if you look at the fifth description about computer architecture, it actually tells you that computer architecture is the manner with which the components of a computer or computer systems are organized or integrated. So this is computer architecture. This is computer architecture. Okay, and computer architecture are very important. And important in a way that is as important as those hidden figures in NASA. And recently people start to recognize the value of computer architecture. So here are some video clips that, well, so first of all, right, let's talk about fake human beings like Bard and ChatGPT. If you ask them about like how important is computer architecture in computer science, that's what they would say, right? So they would say, well, computer architecture is very important, right? In certain ways, if you don't trust me, open up your browser and either Bard or ChatGPT. And I don't want to tell you my personal preferences using Bard, but you can use ChatGPT if you want. And they will also tell you that computer architecture is very important. And let's talk about real human beings. So what's the foundation of deep neural network? Well, machine learning right now is the deep neural network, right? So do you know who are actually building the foundation of deep neural networks in the recent decades? Who did that? Machine learning, like.
I'm not sure if this is exactly what you're talking about, but you're talking about how it's like supervised learning, how humans give feedback to.
I'm actually saying about like who are the key researchers build the foundation of deep neural networks nowadays. You guys know their names?
It's all the aggregate data from Google.
Yeah, but the names of the humans. No.
Excuse me, Professor.
Yeah.
I think there's some slight audio quality issues for our online guys. We can hear you all right, but it's not super clear. We're wondering if there's a microphone.
Yeah. Okay. So this is an issue that I have to deal with this classroom. One thing that I could do is that I can purchase a microphone later, but there's nothing I can do for this particular lecture. Sorry about that. But okay, by any chance, okay, anyone who can Google who won the Turing Award in 2017 for deep neural networks? Yang Kun. Who else? Yeah, who advised Yang Kun? Who is the advisor of Yang Kun? Yeah, there is a microphone here. Let me see if there is anything I can adjust. Yang and who? No, S-bar. All right, so all right, so this is actually a video clip that I cut from the Turing Award ceremony, the Turing Award speech in 2017, for Turing Award 2017, and that was actually for deep neural networks, and this guy is Jeffrey Hinton, and he is actually the advisor of Yang Kun. And let's hear what he said about why deep neural network can finally success.
I think a lot of the credit for deep learning really goes to the people who collected the big databases like Fei Li, and the people who made the computers go fast, like David Patterson and others.
Okay. Did you hear that? Do I need to play it again? Let's do it one more time.
Credit for deep learning really goes to the people who collected the big databases like Fei Li, and the people who made the computers go fast, like David Patterson and others.
All right, did you guys hear that? A lot of credit goes into what? big database like people like Fei Li, and people who make computer skills faster, like Debbie Patterson. Have you ever heard about the name of Debbie Patterson before? Really? Okay, look at this. What is this? It's in your textbook, right? Look at the name. David Patterson is right here, right? So actually, what it implies is that without the advance of a computer architecture, there's no way deep neural networks can success. So that's actually a very important thing, right? Why you should care about computer architecture? Because that's the foundation. It's like a vehicle driving the advance of computer science. So if you cannot make your computer faster, a lot of things won't happen. So, and some of you might still feel like, okay, why should I care, right? The algorithm will probably help me a lot. So here I'm showing you a quick demo. So for this pieces of a code, tell me the algorithm complexity if the variable option is set to 0. What's the algorithm complexity if the option is always set to 0? The complexity of the algorithm.
I think it's all in modern.
It's all of log of y.
Uh,
If option is 0.
yeah, because it's not sorted, so
It is not sorted, so it's order.
it's and small.
Is order n. Agree? All right. But and if option is set to 1, then it will be order lib and log n. Right? So what does that mean? Is that okay, if option is enabled, if option is set to 1, then the complexity is higher. And I have to do more stuff. Right? And if the algorithm is if it's set to if it's set to 0, then the complexity is actually lower. Do you guys agree with that? Okay, so let's see how does that reflect to real application performance? So in this class, we will use Jupyter notebooks a lot, and including your 142 lab. So here I can show you a quick demo. So for this program, this is exactly the program that I show on the slide. So as you can see, right for here, I have a variable called option, and if option is set to 0, then I won't call this sort, right? And if option is set to 1, then I will call this sort, and before I call this calculate sum function, right? So let's see what's the how much time it takes to execute the program. And then right now, let me compile the program so you know it's on the fly. It's not something that I have cheated. I'm not cheating on performance, right? So right now I run it for the first time. I run it for 256K elements, and for 1,000 iterations. And I set it to 1, which means that I'm sorting before running a calculate sum function. So as you can see on the screen, it takes 0.16 seconds to execute the program. So right now, I'm running it with the last argument, which correspond to the option as 0. All right, so if you look at that now, right, it takes 0.57 seconds to finish the program. Even though its complexity is lower, even though it's doing fewer things than option is enabled. Does that make sense? Doesn't make sense, right? So, that's one thing you want to, that maybe one thing surprise you. And the other thing that we can also try out, let me do this. Okay, another demo that I want to show you right now is this. So, well, sorting is very important, as we can tell, right? And the one that you guys are most familiar with is probably quicksort, right? Again, what's the complexity of quicksort? N log n, right? So we actually have another sorting algorithm called Platonic sort that I want to put into comparison for today. So this is the code for Platonic sort. And if you trace the code carefully, you'll figure out this piece of code is actually an n log squared n algorithm. And let's take a look of how this algorithm compare against quicksort on GPU. Okay, so let's compare against, so this is the pieces of code that I have. And so let's look at this. This is a, wait, so this, oh, sorry, wrong page. Okay, so this is the quicksort code and on GPU. And this is the Platonic sort code on GPU. And again, I will put all the stuff on the GitHub and you will be able to find a link on our website. So if you cannot capture, if you don't have time reading through all the code, that's fine. And so right now, if I run the Platonic sort, as you can see, it takes 0.4 seconds. And right now, let's use the quicksort and see how much time it takes. All right, so you know when I click is cute, right? The Platonic sort is almost like this response immediately, right? But for the quicksort, it's still running, right? And you might think, okay, what kind of GPU are you using? So here's the GPU that I'm using right now. So this is an NVIDIA 4070, the latest generation 8 levels. And right now, you can see, right, for the quicksort, it actually takes 22 seconds to finish execution. So I'm showing you right now 2 examples that breaks our lovely computational complexity, which tells you that, in front of a computer architecture, algorithm is actually useless. When you talk about performance, algorithm complexity is not the only thing you should care about. You should actually care about computer architecture more than algorithm. So why? You might say why, right? So here's the thing. How many of you know this? Okay, a lot of you know this, right? So this is also an animation that I would watch weekly when I was young, right? So there's always a section that, well, guess what is this Pokemon, right? So when you look at the tail, you probably think that, okay, my computer is like a Pikachu, right? So you probably think this is electric type, right? And these are the attacks that I should use, right? So you think, okay, this is how I use this Pokemon for. But in fact, right, your Pokemon may be something like this. Right, this is more like a cycle type, so you should use cycle attack instead, right? So the problem is that, right, most of the time, this is how you imagine your computer is. So you keep using your computer in the way that you think it should act. However, in reality, this is your computer. So, and who tells you the reality about your computer? That's actually computer architecture. So another example that I can give you is like a lot of people like this washlet at your home, right? So, but the washlet is very difficult to use. So if you just sit on the washlet without any control, the washlet is just like a normal toilet without any spatial function, right? Or you want to buy your grandparents a Tesla. One day, if you are rich, do you want to buy them one? No, why? They don't know how to use it, right? So here's the thing, right? Okay, Tesla has a lot of good features, right? They have autopiloting. I tried it, but it's not actually that great. But anyway, they have autopiloting, right? They have a lot of fancy features, right? People love it. However, if you don't know how to use these features, Tesla is probably even worse than a Toyota Corolla in terms of the driving experience. Agree? right? So here's the thing, computer architecture is the subject, tells you about the features of your underlying computer and how to utilize this awesome features to make your computer program running faster. So, but before we start with that, well, since we are here in person and some of you online, you guys can brainstorm as well. So, you have been, like, this is a senior class, so a lot of you probably already have experience in a lot of computer science class. Can you guys, discuss, put together your knowledge and use 3 minutes to brainstorm together with the group around you to tell me how does a computer execute your code. So go ahead, discuss with your friend. If you are not friends yet, this is not a bad time to start being a friend.
I guess. Yeah, no, I think that's probably.
Yeah, it's gonna be regular. But then there's also what they call interpreted. Yeah. Okay, so then that is pretty into like and then it gets compiled and then some gets read out like it's eventually to a popular and then that is really long like then you find I guess yeah, well that's that's I don't think it works after like the objects yeah, that's like yeah, for we that's
All right, it looks like you guys reached some consensus. So, any idea how does the computer execute your code? How does the computer execute your code? Anyone would like to share? Ahmed, right? What? You're done.
Yeah, okay. So like it goes back, I mean, I guess it varies, but right, but like, for example, for C code, right? You take your like source code file, that gets pre-processed to the I file. Then that I believe goes to the that gets assembled into the assembly file. That gets turned into an object file like the machine code. So it turns to an executable. Yeah. Do I hear that?
Okay, so executable and then
it just so you get whatever output.
then the computer can do what? Okay, say that I have a executable file, right? And how does the computer run this executable file? Okay.
So I mean now the operating system comes in. Yeah.
Okay, operating system, okay, 120.
So there's a whole class, right?
Yeah.
And the operating system, what takes the executable, I guess it depends on the operating system, but it would feed it into a page as well, and basically finds ways to store the human level code in memory, and then also.
Okay, where do we store that code?
Somewhere in memory, I guess either.
Somewhere in memory, okay, somewhere in memory, okay, memory. Keyword, memory. And
What?
and what?
I'm not
Okay,
sure which one.
you are not sure. Do you know the then?
I think it links the machine code to the instruction sets and like the operating system tells the ALU what to do.
ALU what to do, okay, so there is an ALU, okay, in where?
In the CPU.
In a CPU, okay, another keyword, CPU, right? Then,
I guess it takes whatever the outputs of the CPU is.
okay, anyone would like to summarize the whole picture? I guess that's my job, okay, so. All right, so, right, so here's the big picture of computer architecture, von Neumann architecture. So, this guy, John von Neumann. So if you want to find one figure in computer architecture, I would definitely say it's John von Neumann. So, what's the contribution of John? So, how many of you heard von Neumann architecture before? Okay, tell me more about it. What's von Neumann architecture? Okay, you don't know what it is.
It's like the fundamental of computer architecture.
It's the fundamental of computer architecture. Okay, okay, glad to hear. What else? Ivan?
No,
Okay, so John von Neumann say this, right? So if I want to build a computer, here are the components that I should have. So 3 types of components: processor, memory, and persistent storage. And why we need these 3 different components? First, if I compile a program or if I have data that I want to store persistently, right? Then I put them in a persistent storage. And whenever I want to execute the program, the computer should try to load the whole program, both the instructions, which are the commands that you want the CPUs to execute later, and the data which you want the CPU command to operate later. Both of them, put them in memory. And then when it's scheduled to execute this program, your processor will fetch this instruction from specific memory location. And then once you fetch this instruction into the processor memory, you look into this instructions and see what commands you want your CPU components, for example, the ALU or maybe the memory unit to execute this instruction. So if it's an arithmetic instruction, you just use ALU with your content in the register to generate the output. Otherwise, if it's a data memory access instruction, then this instruction would have to interact with the memory to fetch the data from the data memory to the processor for later processing. And once you're done with an instruction, you keep fetching another instruction. So the good thing about this computer architecture is by loading different programs into the memory, your computer can perform completely different functions. That's the beauty of von Neumann architecture. So you are probably too young to know this. So how many of you played arcade machine before? Okay, right. So what makes arcade machine different from the game console except for it's larger?
What the experience?
Experience, okay. What else?
Rent terms. You pay like a quarter or whatever.
Okay, you pay, okay.
You can only play that game.
You can only play that game, right? So that's actually a big feature of arcade machine. So in the past, you can consider before von Neumann architecture, every computer is pretty much an arcade machine. So if this computer is built for calculating mathematical numbers, that's the only thing it can do. You cannot use that computer to play games. If this is a computer built for gaming, it cannot be used for spreadsheet, it cannot be used for web browsing. However, the beauty of von Neumann architecture is that, okay, we just put this three components together and just try to load different programs. Your computer can be a gaming machine in the night. It could be a business machine during the day. That's the beauty of von Neumann architecture. So that's why von Neumann architecture becomes the dominating architecture in all computer systems. So right now, if you have a desktop computer, you can see it has a processor, it has a memory slot, it has a peripheral slot, and the peripheral slot is typically used for like storing persistent data or interacting with your real world, right? And if you have never seen the real hardware, that's another benefit of in-person class, right? So I brought something for you today. So I forgot the red module, but see if I can take this down. This is a okay, be careful. This is a computer that I still used a couple days ago. And yeah, although I already retired this computer, but I plan to sell it on eBay. So don't that might, I'm paying mortgage now, so. Okay, you have to think about everything, every penny you can earn. Okay, so this is a heat sink. Typically you put it here on top of your processor. And the reason is because the processor nowadays are really hot. So you really need some kind of heat sink. So if you don't know what a heat sink looks like, that has this along. And this is the motherboard. And as you can see from the motherboard, be careful. The back end has a lot of pins. So be careful when you have it. So this is the CPU slot. And as you can see, you can take this off. And then inside here, there is a processor. And this is an Intel Core i5 9600 processor. And on the back, there are a lot of soldering pins that you can actually connect with communicating with the motherboard. Pass this around, be careful though. And this is the motherboard. As you can see, there are some PCIe slots here. And typically what you would do most of nowadays, this is one of the most common type of PCIe peripherals that you will have attached to your computer. That's a GPU. So this is also an AMD GPU that I retired a long time ago. So this is what I cannot really see it. So this is a GPU, and GPU is also very hot. So as you can see, there is a heat sink, and under the heat sink, this is actually the core of the GPU chip. Pass this on, and this is you can also put a cable connect with this peripherals, and this is an SSD 2.5-inch SSD. So that's where you can put your data. And if you're interested about what a motherboard looks like, pass it around. And right, so this is your computer. But what the most important thing, that I want to tell you is that every computer, desktop computer, has a processor, has DRAM, has peripherals connectors to your persistent storage. So it's a von Neumann computer, right? And if you look at a server, right? This is a server motherboard, except for they can accommodate more processors, more DRAM slots, and more peripherals. It's again processor memory storage, right? Okay, MacBook 13-inch. That's actually the one that I have. If you tear it down, which I didn't do it, otherwise my warranty will be gone. It also has a processor plus GPU module, solder DRAM, which people hate it. I hate it too. And solid state drive for persistent storage, and a lot of Wi-Fi modules for you to communicate with the rest of the world. And iPhone 14 Pro, I'm thinking about getting a 15 for sure this year, right? If you have an iPhone 14 Pro, processor, DRAM, storage, and some other Wi-Fi modules as well. PlayStation 5, how many of you have it? Okay, really? Seriously? what game consoles are you guys having nowadays? PC, okay, awesome. Okay, if you have a PlayStation 5, processor, GPU, DRAM, persistent storage, right? And if you have a Switch, how many of you have Switch? Okay, finally, I have a Switch.
Sorry, I had a question about the PlayStation. The DRAM's in a circle.
Yeah, they solder it in a circle.
Why? Why?
Well, I don't know. Because it's fancier. Okay, so Switch, right? If you have a Switch, right, then processor, GPU, DRAM, and Wi-Fi modules, memory cards for storing data as well, right? So you can see, okay, Tesla. If you have a Tesla, right, processor, DRAM, and SSD, and some power control IC, right? Even Tesla is a consumer computer, right? So that's why every time that you do firmware upgrade on your Tesla, then you will figure out that, well, it's getting more and more efficient. You have some new features. Do they support Apple CarPlay yet? Not yet. Okay, that's the reason why I want to get a Tesla. All right. So, but looking at those examples, right? You know that processor memory are everywhere. Why? Because every computer system, no matter it's a big one, as giant as a Tesla, as small as your iPhone, they are all volume architecture. They are all volume computers. So in volume computers, this is what your program looks like. So this is actually a real program, and if you can use object dump, here's the content of the program. You see a lot of binary numbers here, right? Who they are actually the machine instruction. And to execute this machine instruction, your microprocessor is indeed a collection of functional units. So typically there are 5 types of instructions that you will interact. Okay, so when you're done, where are the stuff? I'll put that in the box. Thank you. Thanks a lot. Okay, so microprocessor is in fact a collection of functional units. So depending on the types of instructions you have, you would have different functional units to deal with it. So a microprocessor would typically deal with logical operations, simple arithmetic operations, or more complex like multiplication or division operations. Or because you might want to change your execution flow. So there will also be branch and jump instructions, and as well as memory operations for you to interact with your memory. And but most of the time, you need some abstraction for you to easily access those instructions. So that's why we have an abstraction called instruction set architectures. So when you compile your code, we are actually compiling your code into comments that this instruction set architecture describes. And when your processor receives that, it will parse what kind of instruction you want the processor to execute and distribute this command to different functional units. So that's basically what a processor is. So if you still feel that, what does this abstraction look like, right? Again, right, go back to your Pokemon, right? If you haven't played Pokemon for a while, take it out, right? You will figure out, no matter what kind of Pokemon you are having, this is for the 4 buttons you have to remember, right? This is the 4 buttons you have to remember, right? So instruction set architecture is indeed like mapping the features of your Pokemon into these 4 buttons, and instruction set architecture is mapping the features of your processors to commands. So, and that's the instruction set architecture. And you will say, well, most of the time I don't program in assembly. Right? I hate assembly. I hate CSE142. I hate that too. Okay, so I hear you, right? So most of the time, this is what I do, right? I program in C. I know a lot of you don't even program in C, but unfortunately, that's actually a very efficient language. And I will show you later how efficient it is in C, why I love C, right? But the truth is that, okay, I program in programming languages like C, right? So as you said, right, when you program in C, if you look at that, right, so there will be control flow operations which control the execution of a loop. That's when you need conditional jump instructions. You will have logical operations. That's when you need logical instructions. And you will have arithmetic operations. So that's why you need arithmetic instructions. And you store data in an array, which is consecutive locations on your memory. So that's why you need memory accesses instruction. So with this, right, your high-level language expression will be going through a process called compile. And the one who compiled your high-level language is called compiler. It will translate this human readable programming language representation into instructions, as you can see on the slide. And there are also data, static data, for example, that the compiler would take and store it somewhere in the memory as well. So a program, a complete program actually contains two parts. One, instruction, and the other, data. And how the C code becomes a program is actually going through the following process. So first of all, you write your source code, use a compiler called GCC or something else, and it will generate the program with instructions and data, as we mentioned. And as some of you mentioned, right, most of the time I don't write those like sort function myself. I call external libraries. So it's also the responsibility of the compiler to figure out when you want to execute a program, where can I find those libraries that you would use when you execute a program, and then link them when you execute them. And once you want to execute the program, we link those libraries together, together with the compiled binary code and put them in the memory. That's exactly the Neumann architecture, right? Some of you saying that, okay, I hate C programs, so I write in Java because they have elegant object-oriented programming style. Okay, I know your feeling, right? I hate Java. Okay, so for Java, it's also a Java C compiler, but instead of compiling your program directly into the machine code, Java has another abstraction called bytecode. But bytecode is nothing more another type of machine code that understood by Java virtual machine. And so when you want to execute a program, it's the Java virtual machine take those bytecodes and translate those bytecodes into the machine code for the processor to execute. So that's Java. And finally, okay, most of you probably use this language now, right? Python. So Python is an interpreter-based language. So what happened is that, okay, I take the Python code, and there is a something called one-time interpreter. It will generate a machine code on the fly, and then put this generated machine code into a memory. And again, it's still the Neumann architecture. Your processor fetch the compiled instruction and execute them together. Okay, so it sounds like Neumann architecture is awesome, right? So one thing that people always love about Neumann architecture, especially in the good old time, is that once I'm done with my software programming, as long as the processor goes faster, then my program will go faster. Because if you see the nature, right, it's the processor execute the program. Right. So as long as your processor goes faster, your program goes faster. Agree? Okay. But if you look at the trend of performance evolution, so for this figure, the horizontal axis is the year, and the vertical axis is G plus some kind of metrics represent the computation capability of your processor. So in the past 8 years, the CPU performance is only improved by 3 times, which is very, very slow, right? Why? Because there are challenges from Neumann architecture. But before I tell you the challenges of computer architecture, can some of you tell me, from your understanding, from your readings, from the social media, what's the reason we don't see processor getting improved? What's the main reason? Power and heat. Power and heat. Okay, perfect answer. What else? What? Cost, okay?
Isn't that, I think, the Moore's law kind of starting there?
Okay, that's actually a lot of people would say, right? But and that's the answer I really like, but thanks. Right. So here's the thing, Moore's law. So Moore's law is actually a law, it's not actually a law, it's by a paper written by Gordon Moore. Gordon Moore just passed away, I think, earlier this year. And what he mentioned in the paper is that the number of transistors we can build within a fixed area of silicon doubles every 12 to 24 months. So if you don't know what Moore's law is about, let me give you a 20-second recap on Moore's law. And you can claim now you read the paper. So what's the paper of Moore's law about? So first of all, in the first paragraph, it talks about integrated circuits are more increasingly popular. And then they are well established and they are very reliable and they are getting smaller and smaller. And it's easy to manufacture, so you should use IC. And heat is a solvable issue. And designing ICs can be easy, but I don't think you agree with that, right? A lot of you took 140, you hate that. I understand. And they are widely applicable, right? So that's actually the whole idea of Moore's law, right? So, but the most important thing is that Moore's law is actually projecting because the IC are getting smaller and smaller, and you draw a line saying that, well, look, the trend is that we can put more circuits within the same area every 12 to 24 months. So, you know, this is an era that we have a lot of, I would say, fake news from social media, and even a lot of high-tech people, they are lying. I don't want to tell you who, but whoever said Moore's law is dying, they are lying. All right. So why? So here's the figure that I draw. The horizontal axis is the years from 1970, and the vertical axis is the transistor density per millimeter. So the dots here are the chips that we manufacture. They are real products from Intel and many other companies. So if you draw a line, this is a straight line. What does that tell you? Is Moore's law dying? Moore's law is living perfectly well. We are still allowed to put more and more circuits within the same area. Moore's law is not dying, right? But the thing is what? The thing is what? Moore's law is not dying, right? But as, what's your name again? Jack? Okay, as Jack just mentioned, right? It's actually the heat problem. So although Moore's law is not dying, right? But the power density of processors are actually going up a lot. So in the past, you can use the processor to cook an egg, but you know, recently the density is very close to a nuclear power plant. And if we keep having the clock rate going up, if we don't do anything, then at some point people were projecting that it could be as hot as the sun's surface. But it's not, we didn't reach that point because after people identified that issue, we start to slowing down the growth of clock rate and slowing down the per core performance of your processors. So that's why we don't see the processor are getting improved. So and actually, even though Moore's law is not dying, but single core scaling is dying. This is the right-hand side is Gary Patterson, the left-hand side is John Hennessy. They are actually the Turing Award winner for 2018. And let's hear from them.
So the first thing to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
Right, so they tell you that single cores are not getting any faster, right?
The future is parallel.
Single cores are not getting any faster.
Okay, so the truth is that single core performance are not getting any faster. So after the way how we control the density problem is that instead of increasing the clock rate of a single core processor or making a single core processor faster, we start building multi-core processors. And right now, if you buy an Intel processor, you would typically have like more than 8 cores, right? And so multi-core processor is everywhere. Like your iPhone, it has 4 cores at least. If you have an Android phone, because they cannot make their processor single core performance better than Apple, so they would do is putting more cores there. And the thing is that, okay, if you look at NVIDIA's architecture, right, we still have no trouble putting more transistors. If you see the transistor count, they keep doubling the transistor count every generation. But what they cannot control is the power consumption. So for the Turing architecture, is actually 315 watts in their data center architecture for the B100. And for the A100, the Ampere architecture, it takes 400 watts. And for Hopper architecture, it actually takes 70 watts. So what actually improved what actually affect the cost is that this is the product photo of A100. So you need a 2-slot piece thing. But if you want to dissipate the heat generated by an S100, you actually need a multi-layer heat sink like this one. So it's actually not very controllable. So that's why they don't put S100 as the architecture for the end user product. Instead, they give you ADA loveless, which is an improved version of Ampere architecture. So, but even with GPU, is it enough? The answer is no. So that's another figure that I draw. So the horizontal, well, so you already see the blue line, that's the CPU performance. And someone who is selling GPU always talk about like, okay, GPU are the ones we keep maintaining the Moore's law, we keep maintaining the scaling of performance. But if you look at that, right, they are doing better than CPU, but still only 8.5 times for 8 years. Okay, what's the demand? So if you look at the growth of G blocks, okay, so here's the red line is the demand of AI models if you want to finish training a model within a week. And there is also another law, so people love laws. Demand of AI models double every 3 to 4 months. So in the past 8 years, we are actually 42 million times demanding than the past. And in the meantime, your GPU is only fast by 8 times. So that's not going to be good enough. So right now in your computer architecture, in addition to processor memory storage, we start to have a lot of other accelerators like GPUs, FPGAs, or tensor processing units. But there's also another issue because everyone has to access data from the memory. And if you look at performance between processor and memory, there's actually a significant gap between them. Right? So you can think about that. Okay, even though my unit is running really fast, but I have every time when I need the data, I have to pay like hundreds or thousands of cycles to get it. That's not fast enough. So those are the issues of computer architecture: slow memory, data movement, and slow improvement of processors. So this class is going to tell you how we can make our program faster in this era. But the reason why you are here for the first class, I know a lot of you like to hear this, right? What's going to be in the class? So we are going to talk about performance. We are going to talk about memory. We are going to talk about parallelism. We are going to talk about processor design. And here's the schedule you can find online and from our website. And for website, you can find an identical table like this. We have topics, we have your reading, we have slides, and we have due dates. And if you check the topic, we are actually going to cover performance, memory, processor, and parallelism very well. So in this class, we are going to learn all of sorts of things. Okay, finally, most importantly, learning experience. So we have in-person section, and I like you guys to, well, if possible, I know people love online. I appreciate that too. And also, if you are more interested about in-person, feel free to come by in class. And for in-person sessions, we are going to be more interactive. And the reason is because when I was a student, right, I feel like most of the classes are like watching TV forecast, right? So you just look at TV and you feel like, okay, boring, boring, boring. You feel sleepy, sleepy, right? And then, well, you know, what people would do is turn off the TV, right? And what you would do is that I just don't go into classroom. So for me, I like the lecture should be like a game show, right? So I'm the host and you are the participant, right? And everybody enjoy the lecture. So here's our method of teaching, peer instruction. And so for peer instruction, you are thinking about that. You are attending a game show. And if you are attending a game show, you want to win a prize. And so definitely you want to get prepared. So the way how I force you to prepare, and this applies to both online and in-person sessions. So if you think, oh, no, I'm online session, it's not about me, right? No, I still want you to do this. You have to complete the required reading before the lectures. And during the lecture, I will bring some pop-up questions for you to brainstorm. And first, you will individually thinking about the answer of the question. And then we will have a group discussion and a whole classroom discussion. Then we can figure out that, okay, what are the common fallacies that you have and help each other understand better. So this is a process of read, think, and discuss. And so before the lecture, we have reading quizzes, and there's already one online on Canvas. So if you look on log in to Canvas, that's where you can find. And it's based on the assignment of reading from your textbook, Computer Organization and Design, and by John Hennessy and Gary Patterson. And sometimes I will pull off some assigned materials. And some people already email me like, do I really need a textbook? So my answer is, I know textbooks are expensive, right? But the purpose is that whatever you can do to retrieve the same material as the section assigned, it's up to you. If you want to purchase the real book, okay? Is that clear enough? All right, don't ask me the question again. And I will try to. I know this is summer. I know you are stressful, so I will try to have the reading quizzes about like twice a week. Okay, and every reading quizzes you will have 2 chances, and we take the average. And there's no time limitation until the deadline. So because all the purpose of reading quizzes is that at least you go through the material so you know what's covered. So it's okay for you to open your book, look at the question, figuring out where the answers are, right? And but again, because the purpose of the reading quiz is to prepare you for the lecture, so we don't allow makeup reading quizzes. But sometimes you might feel like, okay, I'm sick, I'm tired, right? So we will drop your lowest 2. So if you miss 1, never mind, we will drop the missing 1. And if you miss 2, never mind, we will drop the missing 2. If you miss 3, okay. Right. So peer instruction. So we will have an experience of peer instruction in the next lecture, and we will use a software called Paul Everywhere. So if you have any kind of smartphone, or even you have your laptop, bring it and install the app, or go to the website. And I already pre-registered every of you, so you should be able to log in. If you can't, let me know. And every time when you go to the lecture, make sure that you log in the app through your UCSD account and join this website. And but again, every time when I have the pop-up quiz, I will put the QR code and the address there, so you don't have to do it right now. And most of you care about this, right? Great. So we have 2 sessions. We have in-person session and online sessions. And for online sessions, again, for online session, well, first of all, some of you were curious about are we recording the lecture? The answer is yes. So every lecture will be recorded, broadcast likely through Zoom or YouTube. And if you're on YouTube, you probably won't be able to interact with us. But if you are on Zoom, feel free to unmute yourself and ask questions anytime. And for everything will be in my YouTube channels. Even though you are in person, you are free to watch the YouTube playback. I love YouTube. I want to be a YouTuber, but you know, too difficult, right? And online session because you're not in person, and I know a lot of people take online session because you don't have time to come to the class. So there's no participation grade in online session, but we will put more weights on your midterm. So for online session, your midterm will worth 30%. For in-person session, your midterm will be 20% and plus 10% of in-person discussion. And for the in-person session, as long as you answer 50% of the question, you will get full credit. Right. So if anyone online, if you are in town, if you think you can make the time, you can show up at least 50% of the time. Feel free to switch in person. Or if you feel like, okay, I'm shy to talk, right? I want to switch to online. I'm okay with anything. All right. And but other than that, reading quizzes, 50%. Assignments, we will have 20% of assignments, and the TA is going to cover the discussion session. TA is going to tell you how to do the assignment, how to ace the assignment, and we will drop your lowest assignment. So we have a total of 5 assignments assigned throughout the quarter, and even though you are not performing well in one of them, or in the first 4, you think, okay, I got 4 credits in the first 4, you can drop the last one, right? And final exam, both in person and online, works for 35%. And I know online session has a lot of more resource when you are taking exams, so we will definitely have different versions of that. And for people in person, I know you have limited resource, right? So you know what I mean. Okay. So assignment is typically assigned on Wednesdays, due on Fridays, and everything is submitted through Grayscope. And I want you to type because there are too many issues with your hand freedom. Especially a lot of our TAs cannot recognize your lovely handwriting script. So that's why we have the assignments. Logistics, this is me, and we have 2 TAs. First of all, I will have okay. So for the TAs, we have 2 TAs, and they will hold office hours on Zoom. And okay, so it looks like Leon is a police guy. And Jerry is a gold guy, right? So if you have this, hobby, talk to them. And discussion session Wednesday 4 p.m. to 5 p.m. Paper Canyon Hall. Check the location on the web, right? And if you log in our website, there is a join calendar that you should subscribe. It has all office hours, both the lecture and the lab, and we try to not overlapping the lecture and lab office hours, so you can get full coverage, as you can see, almost every day, right? Some of them are in person, some of them are online. So just check those events. If it's in person, they will tell you the location. If it's online, there will be a Zoom link inside. And check your grading on Canvas and summary of resources. We have lectures on Zoom, YouTube, and slides on the course webpage, discussion on Piazza, and grading on Canvas, and assignments through Grayscope, and office hour and location through this calendar. The slides will be online. Yes.
So you said assignments assigned Wednesday due Friday, or the following Friday, or is it?
No, the same Friday.
So it's like a week?
No, it's actually 2 days.
I think so. There. Okay.
Yeah, yeah. Okay.
Wait, the assignment 2 days?
Wednesday midnight to Friday. Okay. We will try the first week and figure out. Okay.
Okay.
Other question?
Will the discussion be recorded?
The discussion session will be recorded. I think so. Okay. Other question? Okay. So another thing I want to mention, online solution may not be always true, right? So for example, like even for Bard or ChatGPT, they don't know who I am. So so don't rely on your online resource a lot. And if you have any problem signing to Canvas, email ACMS. Our course infrastructure is on this location. If you cannot log in, email me. Other than that, I think one thing I really like is that I like teaching,
and I enjoy the time that I spend with you guys. And hopefully at the end of the quarter, we can take a photo together and everyone is smiling like this. And that's probably it. Other than that, I will see you tomorrow. All right, last assignment. We have one reading quiz due tomorrow before the lecture. Other than that, I will see you tomorrow.
Like you say, like the separate between the online and in person.